the engineering and science that he's talking about. Charles Park is my cousin. Are you here, Charles? There you are. Charles, you were an alumnus from our department, weren't you? So let's give a hand to an alumnus come back. Kirk was educated as an undergraduate at Utah State and trained as a mechanical engineer, got a master's degree at Georgia Tech in aerospace engineering, and then went to NASA for several years. And it's a pretty interesting thing to have him talk about his experiences at NASA and not being totally satisfied there, finding this new calling in an area of science and technology that he didn't think was really being looked at enough. And he jumped into nuclear physics, got a master's degree in nuclear engineering after that, and will tell us the rest of the story. So let's give Kirk a hand.
Thank you very much. Do you guys hear me okay? Yeah, so I was one of these guys who always thought that I knew what I wanted to be when I grew up. I have my good friend David Rasmussen here, who I've known since I was in junior high, who's also a BYU alumnus, and he can attest that I was one of these guys who thought I knew what I wanted to be when I grew up, only to get about into my 30s and going, you know what, maybe I had it all wrong, and maybe it was something completely different. So if you don't know what you want to be when you grow up, don't feel bad. It took me an awfully long time to figure it out myself. But I'm pretty sure I want to be a nuclear engineer because I want to do things that are going to help us in a big way. Is now the time to push the button? Okay. All right. There we go. I'm going to talk to you guys today about something that I think is really, really important, and I hope you'd agree with me that it's really important to talk about energy. But just before I get started, I live in Huntsville, Alabama, and I'm there because I work at NASA. Do we have anybody else from Alabama in the audience with us today? Raise your hand if you're from Alabama. Well, all B is it two people from Alabama. All right. That's great. All right. That's wonderful. Well, I didn't go to Brigham Young University, but I should have. That was a big mistake that I made. I was tempted away by the promise of a really nice scholarship at Utah State. What I didn't know, though, was meanwhile my future wife was going to school here at Brigham Young University. And so my life could have turned out a lot happier if I would have just known that very simple fact. I could have skedoodled on down here. She reminds me of that. She insists that we're going to make up for all of this when all of the children go to Brigham Young University. So I'm already working on getting T-shirts and so forth to make sure they come here to the physics department and study physics and astronomy, or maybe engineering, that they can't quite hack physics. But yeah, I'm here to talk about energy, something that is very, very important, and it's an awful lot of fun for me to talk about because I think there is a connection here in Utah, and that pleases me to no end because I grew up in Utah. I grew up in Davis County, lived here, fifth generation Utah. So even though I live in Alabama now, I don't think that my heart is not still very close here in Utah. Well, what kind of energy should we talk about? Dare we talk about that N-word kind of energy, nuclear energy? Some people have suggested to me it would be better if we had a new name for it, but the thing that's so beautiful about the name is nuclear energy really is the right name for what we're talking about. It is the energy of the nucleus of the atom, the energy that holds the atom together. Around the atom are these electrons, Physics 101, that whiz around the atom, and all of our energy sources today are based on changing these electronic configurations, whether it's these chips and salsa you're digesting right now, or burning some wood in a fire, or watching coal burn at a coal-fired power plant. That's all based on changing the electron configurations of the atom. And there's a certain amount of energy there. There's a lot of energy there. Obviously, lunch would not be working if there was not energy there. Nevertheless, though, within the nucleus of the atom, within the heart of the atom, are roughly 1,000,000 times greater energies that could potentially be accessed. These are the energies of the universe. These are the energies that make stars shine. These are the energies that keep our Earth a living and dynamic planet. And it's only been since the late 1930s that the human race has even known about the existence of this energy source. And to tap it and to go and realize it has been a tremendous accomplishment. And let me talk a little bit, backing up a bit, to why nuclear energy should not be something that you think of as strange or odd or unnatural. I would like to try to make the case to you that nuclear energy is probably the most natural of all forms of energy. And that's because in addition to the sun itself, which we know runs on nuclear energy, when the Earth formed, heavy elements like uranium and thorium were part of the formation of the Earth. And many of these sunk to the center of the Earth, and they were responsible for geothermal heating. So when you hear about geothermal energy, you're actually hearing about stored nuclear energy that was present at the formation of the Earth and is still providing energy to us today. Geothermal energy is responsible for the generation of the Earth's magnetic field. Does anybody know what are some of the good things the Earth's magnetic field does for our planet?
Keep us from dying.
Keep us from dying. There you go. Without the Earth's magnetic field, the solar wind would strip our atmosphere off our planet, and our planet would be as dead as Mars, which is a planet that doesn't have an existing magnetic field anymore. So we should be awfully grateful that this nuclear energy has been present since the formation of this planet in order to keep nice things like our planetary magnetic field going. So remember, things like the decay of thorium and uranium inside the Earth makes the heat, it creates the dynamo, that powers the magnetosphere, that protects life on Earth from deadly cosmic radiation. There'll be a quiz on that later. Okay. But nuclear energy is not a strange or unnatural thing. In fact, it is part of how our planet stays living. Another aspect of this is plate tectonics. As plates move around the Earth, oceanic plates subduct under continental plates, and things are recycled back into the biosphere. The most important of these is carbon dioxide. Carbon dioxide is liberated back in the atmosphere from carbonate rock. If it wasn't for this carbon recycling, actually life would kill itself off because life would lock up all the carbon, this carbonate rock, and the planet would run out of carbon dioxide, which is a funny thing to hear you say right now because we're so worried about carbon dioxide. But in the long run, without this interplay between life and plate tectonics, the planet would also die. So here's yet another very, very important reason nuclear energy is helping to keep our planet a living planet. Without this nuclear energy, again, like I mentioned, we would have a planet that is as dead as Mars. But instead we have a green, beautiful, living planet. And so I hope that as you think about nuclear energy in the future, you will not be turned off by that word, and you will instead think of nuclear energy as a tremendous gift, a tremendous blessing, without which life as we know it would not be possible. And this is even before we got to some of the good stuff. So here we are in the year 2015. Now, how many of you remember the movie Back to the Future Part 2? All right, some of us oldsters. Now, do you remember what year Marty was going to in Back to the Future Part 2? He was going to 2015. And if you were a guy like me who saw that movie in the theater originally, we imagined 2015 would be a really, really cool year. There would be flying cars. Most importantly, what was the neatest thing about Marty's car? Was it that it flied? Mr. Fusion. Marty had a portable fusion reactor on the DeLorean, which was almost even cooler than the fact that the DeLorean could fly. And we watched that in 1989, and we thought, yeah, for sure, that's totally going to happen, right? Well, here we are in 2015, and what are we burning? Coal. It's not Mr. Fusion. Nevertheless, in all seriousness, our society runs on affordable, reliable energy. I mean, how many of you would want to go to a hospital that you didn't think had a reliable energy source? How many of you would want to do business with a company that you didn't think had a reliable energy source? How many of you can do well in your day-to-day life if the power was going on and off a couple of times a day? The answer is it's just not going to work out. It's just not really feasible. And so that's how things are going to go. But right now, we are shutting down some of the most reliable energy sources in our country, particularly coal. This is an old graph that talks about how 27 gigawatts of power generation from coal is going to be shut down. It's actually a whole lot worse than that. In addition, we are retiring at an ever-accelerating pace our nuclear power plants. These are significant because these are both baseload sources of energy. These are sources of energy that keep things going day in and day out, keeping the lights on. it is very popular to talk about renewable energy sources like wind and solar as a replacement for coal and nuclear energy. But unfortunately, wind and solar energies are intermittent. They are not reliable energy sources. And the cost right now of energy storage is prohibitive. So I would submit to you that this is not the place to look for a replacement of our coal-fired plants and our existing nuclear power plants. We also hear talk about natural gas as a bridge technology to future use of wind and solar. But natural gas is an exceptionally valuable energy source, and many people I've talked to say to use it, to burn it for energy is a waste when we could be using it for chemicals, for processes, for materials, for plastics, for 100 other things that it's so much better suited for. We do have new nuclear power plants under construction in the United States, but they're not being built remotely fast enough to make up for the shutdown in coal and other power plants. So this is not going to be a solution for us. Our Department of Energy puts the onus to fixing this problem on industry. They say it is your responsibility to go and identify new energy sources, new types of reactors, to figure out what should be done. This is a relatively new development. For many decades in this country, our government made all the decisions about how nuclear power was to be developed. And in the beginning, right after World War II and the Manhattan Project, does anybody know what their top priority was?
Bombs.
Bombs. Weapons. That's what it was all about. And this skewed the development of nuclear energy considerably. It also scared people to death because in the 40s and 50s, the view of nuclear meant weapons, destruction, apocalypse, war. I grew up in a time where, a lot of us didn't think we were even going to go to high school. We figured that the world was coming to an end. The Soviets and the United States were going to nuke each other, and I'd never even get a driver's license. And then when I was about 16 years old, the Berlin Wall fell, and Eastern Europe turned away from communism, and I remember thinking, wow, we're going to live. Now what? I think, I wish I could kind of convey that sense of almost resignation and dread that so many people in my generation felt, and the relief that we felt when we realized that the Cold War was over and we were going to live. That said, that era of nuclear fear pervaded, and still pervades for many years. So let's talk seriously about nuclear energy and where it comes from and what we could possibly use. Nature has gifted us with 3 nuclear fuels. There's thorium, and there's uranium, and there's 2 kinds of uranium. Most of the uranium is what's called uranium-238. That's the big purple part. And only a small amount is uranium-235. Now, uranium-235 is special because it's the only natural material that is ready to be used as nuclear fuel right now. But as you can see, it is less than 1% of the content of uranium. And in addition, even all the uranium itself, there's 3 times more thorium than there is uranium. So, if we were to be able to use this thorium and this uranium and extract all of the energy out, let me paint a picture for you. Imagine an average cubic meter of continental crust of the Earth, anywhere. Out in the desert, the mountains, doesn't matter, anywhere. On average, within that cubic meter is about 2 cubic centimeters of thorium and half a cubic centimeter of uranium. If you could extract all of the energy out of that material, the energy content of that would be equivalent to 30 cubic meters of the finest crude oil or coal that we have out there. So that means every piece of dirt anywhere on this planet is more valuable as an energy resource if used as a nuclear energy resource than the finest chemical energy resources we have anywhere. And this is something to think on for just a moment because it means that we don't have to have an energy crisis ever if we use nuclear fuel efficiently. Now that begs the question, do you think we're using nuclear fuel efficiently right now? No. In fact, we're using nuclear fuel incredibly inefficiently. We need to change that. Don't worry, I'm going to tell you how to do it. The path was set by a brilliant man named Glenn Seaborg. And he was a young chemist. He was 30 years old. This is 1942 in Berkeley, California. And Glenn Seaborg was investigating what happens to uranium and thorium when you hit it with neutrons. And he found out that it was possible to convert thorium into a nuclear fuel. If you struck it with a neutron, it would turn into uranium-233, which was a nuclear fuel. And you could strike it with another neutron and it would fission and it would give off more neutrons that could continue the reaction. He also discovered that you could do the same thing with uranium-238. Strike it with a neutron, make plutonium-239, and it would fission. So for the cost of 2 neutrons, you could turn all of that thorium and uranium into fuel. And that was tremendous because now he'd taken us past that little tiny sliver of fuel into being able to use all of the material for nuclear energy. How to realize that vision before of turning worthless dirt into an energy resource. Seaborg was so taken by this realization, it was so compelling to him, that as he wrote in his journal on November 1st, 1944, of this discovery, it was almost more than he could contain. And I have to believe the same thing. You know, World War II was fought in large part because of the belief that resources were limited. That in order for me to have enough, I have to take away from you, or I have to kill you, or I have to destroy you. That is a terrifying and very destructive way of thought. But that is a way of thought that caused us to fight the greatest war in the world with 2 very, very determined enemies. It was energy. It was access to energy. It was the ability to use energy, and the belief that we didn't have enough that started that war. So here's Seaborg sitting in the middle of this war realizing there's enough energy for everyone, enough energy to last forever if we just utilize what we have around us. Very compelling idea. Now, the trick, though, was there was a difference between thorium and uranium. The uranium, when it turned into uranium-233 in fission, it gave off about 2.3 neutrons on average, accounting for absorption and so forth. That was enough to keep things going, because remember, it takes 2 neutrons to get it going. The plutonium, on the other hand, only made 1.9. That's not enough. That wasn't enough. And so we realized there was a difference there. Thorium could be a sustainable energy source. Uranium could not. There was a trick. There was a way to make uranium work. The trick was to use a fast neutron to fission the plutonium. If you did that, then you got 2.3 or more neutrons, and you could make uranium into an energy resource as well. And this is why some of you might have heard of fast breeder reactors. This is why people have thought about fast breeder reactors, which was to utilize the energy of uranium by using a fast neutron to do the fission. And there's a real downside to that, because when you use a fast neutron to do the fission, and I'll skip a lot of physics and cross sections here, and I'll just tell you, it takes hundreds of times more fuel to have the same reaction rate. This represents what plutonium looks like to a thermal spectrum neutron. That represents how many plutonium atoms it takes to achieve the same effect with fast spectrum neutrons. Fast neutrons are not nearly so readily able to cause fission. So the disadvantage here is if you build fast breeder reactors, you've got to use a lot more fuel for a given amount of power generation. That's a disadvantage. It's also a disadvantage you can't build those reactors in what's called their most reactive configuration, which means any change is going to cause them to shut down. That's the way you want nuclear reactors to run. You want them to run in a way where if you change anything, it's going to turn the thing off. And you can do that today. All our reactors are built that way today. If you change them, they'll turn off, which is a good safety feature. You can't do that in fast spectrum reactors. So that's why if you can use a thermal spectrum reactor, you want to. Where does this all lead? Well, it leads that we want to use thorium. We really do want to use thorium because it's the only sustainable nuclear energy resource that works in these inherently safe thermal spectrum reactors. That's why we want to use it. Not because it's 3 times more abundant, not because it has a super cool name named after a superhero. Although that is a really cool reason. It's because it will be sustainably fissioned in a thermal spectrum reactor. I know people who like the superhero thing, they won't go for that. But nevertheless. Okay, so here's the details, because there was a professor in here that wanted to make sure that we had done the numbers right. Here it is. This is for you. So thorium-232 absorbs a neutron and becomes thorium-233 for just a few minutes, for 22 minutes before it decays to protactinium-233. Protactinium-233 lasts a lot longer, turns into uranium-233, which will fission 91% of the time you hit it with a neutron, producing sufficient neutrons to 2.5 neutrons on that average. So multiply 91% by 2.5, you get about 2.3. That's above 2, which is the number that matters, and you win. All right, 2.3 greater than 2. Easy math. Even my grade school can do that. The other really cool thing about this approach is we can drastically reduce the amount of long-lived waste that is produced, almost to the point where there's none. In today's nuclear fuel cycle, we only burn a small amount of the nuclear fuel because of that problem I just explained with plutonium. We can't make enough neutrons to keep burning the plutonium. Just doesn't work. And meanwhile, we're making more and more of this transuranic nuclear waste, plutonium, americium, curium, etc. If you take the spent nuclear fuel out of our reactors today, and you wait for it to decay until the point where it's at the same radioactivity level as it was when you dug it out, it takes 300,000 years. That's a long time. All right? On the other hand, if you run a reactor in a way where you don't produce anything but the fission products, the actual products of the fission reaction, that will decay to stability in 300 years. 300 years. I like 300 years a lot better than 300,000 years. And that's the kind of goal we're trying to go for, is to get that waste toxicity down to 300 years. In fact, I was in Italy last week. I stayed in a place that was a lot older than 300 years old. We know how to build things that will sustainably, safely keep things away from us for 300 years. That's not hard. We're not very good at figuring out how to build things that are going to keep things out of the environment for 300,000 years. That was the Yucca Mountain Challenge. That's been the great challenge. So if we go to thorium, we can achieve this goal because we're starting 6 atomic mass units lighter than uranium. And on our first jump of absorbing a neutron, we're going to be able to get 90% fission. So imagine a freeway, you got 100 cars, and there's the first exit, and 90% of those cars are going to exit at the first exit. All right? And then the cars that are left, 2 more exits down on exit 235, another 85% of what's left on the freeway is going to exit. How many cars do you have left by the time you get to exit 237? You only have 1.5%. 1.5% makes it to that first step, that first transuranic Neptunium-237. And even Neptunium-237 is a useful product. Anybody heard of the Pluto mission? Anybody thought that was pretty interesting? Only one person saw the Pluto mission. Come on, guys. What were you doing on July 14th, 2015? Of course you were looking at Pluto, right? All right. How did we get Pluto pictures? Anybody know?
Radioisotopic generator.
Radioisotope thermoelectric generators. Very good. All right. Plutonium-238 and radioisotope thermoelectric generators. How do our Mars rovers drive around?
Same deal.
Hey, who saw the movie The Martian?
Plutonium.
What does he do when he gets really cold? He goes and he gets the plutonium. And ironically, they presented like it was hazardous. It would have been completely safe. He was under no danger whatsoever because plutonium-238 is an alpha emitter, and you can shield it with a piece of paper. It's very, very good. True that, guys. I mean, if you could actually hold it in your hand, you would get burned thermally before you do anything radioactively to you because alpha emitters are stopped by your skin. It just doesn't. You don't want to breathe it. Don't get me wrong. But it's not a radio hazard. But yeah, it saved Matt Damon's life, which is really important. Unless you saw Interstellar, in which case Matt Damon needed to kill Matt Damon. Okay, so we have 3 paths nature has given us. Nature says, okay, which way do you want to go? Do you want to burn the stuff that we only have a little bit of? Do you want to go build fast breeders and burn the uranium? Or do you want to go with thorium? What's the right answer?
Thorium.
There you go. Perfect. All right, BYU gets it. Why don't you get it? But that's not what we're doing today. Today's reactors, we're using solid fuel, we're using uranium, we're using steam. We're doing all this technology. It's interesting technology, it's nice technology, but it was originally developed for nuclear submarines. It was a great idea for nuclear submarines. You know why? Because nuclear submarines float in water. There's water everywhere. Something goes wrong, plenty of water. All right? Big mistake was made when you took these out of the water onto the land. And this was opposed by the guy who invented it, a guy named Alvin Weinberg. He was the inventor of this technology. He said, here's what you want to do in a submarine. They said, let's put it on the land. He said, no, that's such a good idea. They said, be quiet, Alvin. We're going to do it anyway. The other problem with using water is we really don't get very good thermal efficiency. One of the things we get taught as mechanical engineers is the higher temperature at which you can produce heat, the less heat you have to produce for a given amount of work, which is what you want, electricity, shaft power, whatever. If you have low temperature heat, it takes lots and lots of it to get a small amount of work because you're at low efficiencies. So you want to be hotter. You want to produce heat at higher temperatures so you get higher thermal efficiency. A nuclear reactor, in its most basic form, is something that makes something hot. Some kind of coolant gets hot. That coolant goes through a heat exchanger and it gives that heat to a working fluid, which runs through a power conversion system. And you can imagine that energy getting split into 2 flows. Electricity and waste heat. The waste heat is what you see go up the stack. So the higher temperature at which you can generate that thermal energy, the less of it you have to waste and the more of it you can turn into a useful product like electricity. There are 4 basic coolants that were considered in nuclear reactors: water, gas, salt, and metal. And I put them in this 2x2 matrix with pressure on one axis and temperature on the other. What you want is you want to run at low pressures, because that's a lot safer to run at low pressures, and you want to run at high temperatures. And that's where this salt is great. Salt is a chemically stable substance that's excellent at low pressures and high temperatures. Water, on the other hand, pressurized water, we run at high pressures and relatively low temperatures. It's exactly in the wrong corner of the diagram from where we want to be. Salt is in the right corner. So that's the material I want to entrance you with. There's something great about water. Water holds an enormous amount of thermal energy. There's this metric we mechanical engineers love called volumetric heat capacity. It's a big word. It just means how much heat does some unit of this stuff hold. The more it holds, the less stuff you have to pump through to get a certain amount of heat out. And water's really good that way. It beats the pants off lead and helium and sodium, but it's beaten by salt. Salt's even better. So salt has all the attributes we want. Low pressure, high temperature, fantastic volumetric heat capacity. Today's nuclear fuel is built like a fine Swiss watch. Extraordinary precision, pellets and channels and clad and rods and assemblies. I mean, it's beautiful. I have to admit, it's really magnificent. Problem is at the end of a fuel cycle, you got to take all this apart, chop it up, and throw it away. You don't want to build a Swiss watch only to throw it away. That's just overkill. That was a pretty picture of life. Oops, sorry, too far. Salt, on the other hand, gets rid of this whole idea. The idea you're going to use this coolant, and we're going to go and put the nuclear fuel into the salt itself. We're going to dissolve the nuclear fuel, uranium and thorium, into the salt as a salt. Uranium tetrafluoride, thorium tetrafluoride dissolved into salts of lithium and beryllium fluoride. They're chemically stable in air and water. They're not going to burn. They're not going to react. They don't want to react with oxygen because they're already much happier being fluorides. Is anybody here a chemist? Got any chemistry majors in here? What's the most electronegative thing on the periodic table?
Chlorine.
There you go. Does a fluoride want to be an oxide? No. Everybody wants to be a fluoride, though, right? Heck, even xenon wants to be a fluoride sometimes. Okay. So these salts are a fantastic carrier for nuclear fuel. And here's a picture of what's called Flibe: lithium fluoride, beryllium fluoride, uranium tetrafluoride. Without the uranium, it's absolutely clear. It's just like water. Exactly like water. It's really hot. You don't want to drink it or anything like that. But I mean, you pour it around, you can see it's not terribly viscous, and it just looks and flows like water. You put some uranium into it, it gives it this slight sort of green cast. But very chemically stable, very safe. With that fluid at that high volumetric heat capacity, low pressure, high temperature, you can build compact reactors that are very efficient. This is an entire modular reactor design that was done back in the 60s at Oak Ridge National Labs, and it embodies many of the features that we'd like to have. We'd like to build reactors in factories because we can control quality in a factory, we can control predictability. It's hard to build things on site. It's been one of our great challenges in building reactors, is going to a site and trying to build the machine there, rather than having things small enough, compact enough, and simple enough to build in a factory. With this fluoride salt, we can achieve those goals because of the low pressure. It's really remarkable. They're starting to tell me about this stuff back at NASA. We know it's going to work because they did it once before. They built a reactor that used lithium beryllium salt as a coolant with uranium tetrafluoride. This was done at Oak Ridge National Laboratories from 1965 to 1969. It was incredibly simple. It was incredibly safe. It was incredibly stable and reliable. It ran at high temperatures. Here's the radiator. You can see it's just glowing cherry red hot. It was compact. Here's a guy standing on top of the reactor vessel. There's a primary heat exchanger, the pump, etc. I've been to this place in Oak Ridge. The reactor's still there, in fact. Here's the part I love, though. It was very simple to show. I mean, look at this great 1960s control. I talked to guys who worked on this, and I said, what was it like running this reactor? They said it was really boring. Nothing ever happened. The reactor was so well behaved. I said, well, what'd you guys do? They said, well, there always had to be 2 of us for safety. It had to be a backup or redundancy. But there really wasn't much to do. Just watch the thing run. And I thought, well, that was boring for you, but for the rest of us, we like the idea of boring nuclear reactors. Really, really boring. Hollywood can have drama and excitement and thrills and meltdowns and all that stuff. The rest of us would like boring, please. Very, very boring. Boring reactors are good. Boring reactors that can be successfully operated for 20,000 hours or even better. This is one of the things This fellow right here in the picture, he passed away last year, but he ran the program, and he told me this is what he was most proud of, is how they were able to operate this reactor, first of the kind reactor, for 20,000 hours successfully. That was really unheard of for something that was the very first of its kind. Unfortunately, right around this time, Richard Nixon became the President of the United States, and he cut the budget to the Atomic Energy Commission. This really wasn't Nixon's fault. I don't mean to give him a bad time. He just said, listen guys, you need to choose which of your future reactors you're going to go with. Are you going to go with thorium? Or are you going to go with plutonium? Kind of reminds me of that scene in Indiana Jones and the Last Crusade where he has to pick the Holy Grail. Well, they chose wrongly, all right? They chose wrongly. It was all this guy's fault. No shock. He was a real jerk, as you can tell from this picture. No, he was really a real jerk. I've talked to a lot of people. He was a terrible person. So he canceled the whole thorium program so that more funds could go into the plutonium program. They wanted to build a plutonium fast breeder, and they had the gall to locate the thing right next to Oak Ridge National Labs. It was like they were sticking their finger in Alvin Weinberg's eye going, "Ha! We got you, Alvin. No thorium for you. Take this." Here comes the plutonium breeder. But this never got built because Jimmy Carter canceled it. Started a bad dream one night about proliferation, and he got really nervous, and this whole thing got canceled. So, the better question to ask is, why, after it got canceled, did somebody not say, hey, remember that thorium reactor, that one that we were working on, the one that we canceled to build this thing that we didn't do? Can we have that back, please? They never did that. They never did it in 1980, they never did it in 1983, they never did it in 1986. I don't know why that never happened. That's the part that drove me crazy, was trying to figure out, why didn't we go back and reassess that decision? But it didn't happen. In fact, almost nothing happened until, well, I got kind of excited about it in 2000. And I was talking to some guys from Oak Ridge, and I said, well, what's the problem, guys? Why aren't we doing this? What's holding us up? Oh, gas is cheap. People hate nuclear, blah, blah. The big problem is we've got all these papers that we did, and, you know, they're in boxes, and nobody can read them, and nobody can scan them, and blah, blah, blah. I said, well, that doesn't sound that hard. I could probably fix that. And I said, oh, really? I said, yeah. So I went back to NASA, and I talked a friend of mine into putting some money into getting these papers scanned. And I did a favor for him, he did a favor for me, and we talked to a guy, you know, and all this sort of thing. But after about a year, we had these papers all scanned in. I thought that everyone would be super excited in the Department of Energy. I sent a copy to the Secretary of Energy, I sent it to heads of national labs. Guys, nobody cared. Nobody cared at all. Which was really unfortunate. They should have cared. One guy cared, a professor named Per Peterson out in California. He cared, and he used this information to really help take his research in a different direction. So it wasn't that nobody cared, but he did. Well, then a few years later, I was troubled because I wanted this to be on the internet. I wanted people out there to be able to read it. So in 2006, I started a blog, and I put all these papers up there, and I called it Energy from Thorium, because that's really what it was about. It was about making energy from thorium. And over time, people got more interested. People started to read about it. People started to ask questions, and slowly ideas got out. I got a chance to talk about it and speak about it more. But it reached a point where I really needed to make a choice if I was going to get serious about this. And so I started a company, Flibe Energy, in 2011. And the goal of our company was to go and develop this liquid fluoride thorium reactor technology, or lifter technology as we call it, which is the modern incarnation, the modern version of the molten salt reactor work that was done at Oak Ridge back in the 60s. And so we're taking these historic concepts that were done at Oak Ridge, we're trying to integrate them into new and more modern designs, and we're also trying to learn the lessons of the demonstrations that were done at Oak Ridge. And there are a lot of lessons to be learned. These papers were real well. And in case you ever want to read them, they're all on my website. So, you know, feel free to jump on there and get them. One of the advantages I think we have at Flibe Energy, though, is our proximity to Oak Ridge, because there's still so many important things that took place there. They had the first experiments with thorium and uranium-233 in their graphite reactor. They built the first 2 molten salt reactor experiments. And they also had a process to separate lithium, which is an important technology to go into lifter technology. So it's a big deal that we can access them. Another thing that's changed since the 60s is we've seen the advent of gas turbine technology. If you fly in an airplane, you obviously know what a gas turbine is. It's the engines on the back that make the plane go fast. But gas turbine technology has become a much bigger part of our energy generation scheme. We're using natural gas and gas turbine technology together. They have a lot of great attributes. They're compact, they're modular, they have low capital costs, but they lock us into natural gas, which is a bit of a trick. It's fine when gas is cheap, but it's not so great when gas gets expensive. Right now, gas happens to be cheap. Utilities love the fact that you can call to GE and you can build these gas turbine power plants, and it really doesn't take very long, costs that much money. They don't like the fact that when they buy these plants, they're locking into a potentially volatile price source. Let me tell you why you as a customer maybe shouldn't be overjoyed with that either. Because when utilities see gas prices go up, I'm talking about natural gas, they pass those costs on to you directly as a ratepayer. They don't absorb them, they just pass them right through. So when you're in an area that has lots and lots of gas-fired power plants, if gas goes up, you'll see it immediately in your bill. And that's no fun. That's no fun for people that are using lots of electricity, or anybody for that matter. So could we potentially couple the advantages of gas turbines with the reliability of nuclear energy? Not with today's reactors, but yes, with the lifter technology. By coupling the reactor, shown here in a silo, to this compact gas turbine power conversion system, it is possible to imagine a modular, safe, simple, and readily manufactured item that we can build in a factory and bring to a site. This is the layout of the power conversion system of the reactor, showing how the thermal energy generated in the core is transferred in the primary heat exchanger to a coolant salt loop, and then to this gas that operates in the power conversion system. The gas that we think is going to be the best is supercritical carbon dioxide. We hear a lot of bad stuff about carbon dioxide, but carbon dioxide actually has remarkable properties, particularly when you get it close to its critical point. It starts to behave almost like a liquid. And that's a big deal for gas turbine guys, because one of the disadvantages of gas turbines is how much work it takes to pressurize that gas. By using carbon dioxide, we can reduce that pressure work, that compression work, and we can increase efficiency. This cycle would operate at about 45% conversion efficiency. Now, for all you non-mechanical engineers, you have to understand that's really a good number. You know, I mean, you're thinking like students who get 45%. That's like an F minus. All right. You have to know for mechanical engineers, 45% is like, oh, I'm gonna pass out. That's so good. Most of our power plants today are getting conversion efficiencies of 30 to 35%. So 45% is really knocking the ball out of the park. That's a big, big, big improvement. 45% coupled with an energy source like thorium that's so inexpensive is really compelling. Let me talk about safety for a moment, because these reactors possess a really compelling safety feature with their liquid fuel. If everything goes wrong, the reactors will actually drain into a completely separate system, and this is stopped in normal operation by a little frozen plug of salt, just like having a stopper in a bathtub, except this topper is made out of something frozen. You have to keep it frozen. If you stop keeping it frozen, though, it'll just melt and it will let the fluid drain out. Within the reactor, there's two things that make it work, both the fuel and the graphite moderator. When those two are separated from one another, the reaction can't continue. So when the reactor drains its fluid out, it's no longer capable of keeping a nuclear reaction going at all. So that's a really, really nice safety feature. This is a safety feature that doesn't require any operators, doesn't require any electricity, doesn't require any valves. It even works if you severely damage the reactor. So this is a very, very compelling safety feature, all made possible by the liquid fuel. There are reasons to think very seriously about the Utah connection with this technology, and one of them is this big pile of rocks. Okay? Anybody been to Delta, Utah before? I had until a few months ago. Anybody here from Delta, Utah? Okay, put your hands over yours.
On that word? Find something from Delta.
All right, I mean, Delta's like, it's pretty close to the middle of nowhere. Don't say it. Right?
They're from Delta. They're not still there.
Okay. Let me tell you something kind of neat about Delta, Utah. Delta, Utah is the source of 85% of the world's beryllium. Anybody know that? All right. 85% of the world's beryllium comes from, it's processed there in Delta, Utah, comes from a mine 50 miles out of town. Beryllium is one of the essential ingredients to making the thorium reactor work. This big pile of rocks is a pile of barrel rocks. In fact, I think I have a piece of barrel in here I'd like to. It seems a pity we brought it all the way from Alabama and not handed it around. Oh, please don't be the moment I realize I forgot it. All right, it's really great. Just so you know, anybody here like emeralds? Yeah, pure beryl. That's what an emerald is. Pure beryl. And my wife keeps reminding me of that as the beautiful emerald. So yeah, 85% of the world's beryllium already coming right here through Utah. The process that they use, the process is beryllium was developed at Brigham Young University and University of Utah. That's one of the big reasons why Utah has a beryllium industry, is because of work done right here. I think that's worth considering. Up in Nevada, there's a pass called the Lemhi Pass, and in that Lemhi Pass is North America's richest deposit of thorium. In that Lemhi Pass is enough thorium used in this technology to power our civilization for hundreds and hundreds of thousands of years.
Idaho.
And that's pretty exciting too. Idaho, yes.
Yeah.
Idahoans are offended.
Idahoans are offended.
That you said it was bad.
Oh, I said Nevada?
Yeah.
Oh my goodness, I was thinking Idaho. Lemhi Pass, Idaho, potatoes. I was just trying to think of a sports team, but I was just coming on. Is there a sports team in Idaho? There's some cool stuff in Nevada, though. Shouldn't leave them out. There's a great lithium deposit out in Nevada. It's one of the reasons why Elon Musk built his gigafactory. So lithium in Nevada, thorium in Idaho, beryllium in Utah. Anybody seeing a combination here? I think we've got a winning team. What's that?
Perfect script to make a thorium.
Yeah, that's right. We got all the pieces we need. Now we just got to go do it. Now let's talk about where to build the thorium reactor. So here's the Delta guy, all right? This is the Intermountain Power Plant. This is down outside Delta, Utah. Right now they're burning coal to make 1,800 megawatts of power. Unfortunately, this plant is scheduled to be shut down in 2027 because there is a power line from this plant that runs straight to, anybody know where?
Los Angeles.
Los Angeles. So $1 billion of money from Los Angeles is coming into the state of Utah every year because of this plant. And hundreds of jobs are preserved because of this plant. That's a good thing for the state of Utah. It would be even a better thing is if we could do exactly what this plant does right now without that part, without burning coal. And that's what this thorium technology may allow us to do. Is we could, I've talked to the folks that run this plant. It's a great site. They've got cooling water, they've got rail access, they've got the power transmission lines, and they've got plenty of room. If we were to imagine putting a lifter reactor out in Delta at this site, we could preserve that $1 billion of revenue, the water rights, jobs, and the jobs that depend on those jobs, and also the grid stability that this site provides, not only for us, but also for California. We could create new products, new revenue, and be leaders in this new technology. And leveraging the mechanical, and the mineral resources that we have already here in Utah, Idaho, and Nevada, as well as the academic excellence exemplified by this fine university right here. So that is why I am of the strong opinion that BYU and Flibe Energy hopefully have a very bright future together. And thank you very much for having me here today.
Before we get into questions, David Allred is taking Kirk to Gloria's Little Italy restaurant, 5:30, and if you want to be there, you can just show up and join the party. So, okay, now questions.
You get the lights.
So when a power company is looking at doing this at IPP or building a gas-fired plant at IPP, and they look at the construction cost difference, what do they see?
Well, that's not defined yet. I mean, this is still all very, very preliminary. I've
Do
met
you
with
have any idea what it costs to build 1,800 megawatts of this?
We don't know yet. I'm talking with the folks at ITA, Intermountain Power Agency, about this. What they have expressed to me is an interest so far in exploring the possibility of hosting demos. There are earlier versions of this to work towards that goal of having carbon-free energy. But it's down the road. It's down the road.
Are you foreseeing any political boundaries with trying to make this? Because if I remember correctly, that breeder reactors are prohibited in America currently. And so wouldn't thorium technically be considered a breeder reactor in that sense?
They were banned under Carter, but Reagan rescinded that. So no, it's no longer illegal to have a breeder reactor. It just hasn't been done because it hasn't been economically advantageous.
Okay.
But there are a lot of people that think that does. So
What do you think the current limiting factor is to getting this thing moving?
we need lots more smart people like in here working on the project. You know? I mean, lot more of the resources that it takes to go and do the engineering and the analysis to get there, and that costs money. And I'm not here soliciting investment. I'm just stating it needs investment. Yes, ma'am.
So, what resources do you have for us to be part of the solution?
That's a really good question.
To perpetuate, not to perpetuate the idea and influence.
Let me get back with you. That's a very good question. I should have had a slide for that. I should have had an answer for that. I apologize.
We do have a website.
I do have a website, though, but the question she asked is very good because I'm here telling you about how this can help Utah, and I need to have resources and ideas and so forth. Obviously, we're going to have to share this message with a lot of people, particularly people in power. They're going to have to help understand. I think one of the messages I would really like to get out to people is to understand, hey, there's $1 billion a year coming into the state through this power plant, and while we may not want to keep burning coal, we may really want to keep that part happen. You know, that's
Can you
good
write
for-
that down for us so we can all copy it? And that's the primary idea. We need to go tell our legislators, write it down for us. Action plan here.
There we go. That's the part they'll most want to hear about.
And which legislators do we need to speak to? Who's the most influential?
Well, if I recall correctly, the congressman for the 2nd Congressional District for Delta is Representative Chris Stewart. Is that correct? You're from Delta, right?
I'm not sure where the valley is.
Okay. I know he's also the representative for Farmington, Utah, which is bizarre that Delta and Farmington are both in the same congressional district. Nevertheless, they are.
Don't get into that.
But yeah, no, you should be talking to your elected officials at every level, the state level, particularly the state legislature. I think the state legislature needs to know about this because it is such a big deal, not only for the people in that area, but for the rest of the state. It's good it reduces all of our tax burden, it increases our effectiveness of our workforce. It's something that needs to be addressed. Yes, sir.
So regular reactors that are uranium-based, one of the concerns, especially in the context of breeder reactors, is if you know how to make a reactor, then you probably know how to get materials that could potentially be put into bombs.
Mm-hmm.
How does it go for the thorium?
Well, it's interesting. You should read my thesis, which is all about why thorium was skipped over way back in the beginning because it was no good for bombs. That's one of the reasons why thorium got left behind early on in the Manhattan Project, because it wasn't suitable for nuclear weapons. And why, when we talk about breeders today, people are always thinking about fast breeders, they're thinking about plutonium. Obviously, plutonium has been used in nuclear weapons. But we have to have a grown-up conversation someday about where we're going in this world of energy. Because if we decide that we are not going to entertain any nuclear option because nuclear materials have actually been used in weapons before, that's not a very grown-up conversation. You know, we have used chemicals for all kinds of weapons and killed many, many, many millions of people with chemicals, but yet we still use gasoline and all manner of things. We made steel into swords and weapons since the dawn of time, and yet we still use those things. We can take the same fertilizer that fertilizes crops, or we can make explosives with it. In fact, that's how that technology was invented, was for explosives. We can take nuclear materials like thorium, uranium, plutonium, and we can use them for the greater good of humanity, and we can use them to alleviate immense amounts of human suffering, or we can make weapons out of it.
Kirk, just tell them uranium-232 is why it's not a problem. I'll explain it to them later.
Okay. There is a step in the formation of uranium-233 from thorium where another product is made, uranium-232, which has been the poison pill for making nuclear weapons. This is why thorium got skipped over in the beginning. This is the subject of my thesis. And that is why traditionally thorium fuel cycle has been a whole lot less interesting to anybody seeking nuclear weapons than using either uranium or plutonium. But I don't want to demonize any of these materials because all of these materials can be put to great use for the benefit of humanity if we are willing to have a grown-up, realistic conversation about this. Even with today's technology, we are alleviating immense amounts of suffering through the use of nuclear technology. There was a question. Yes, sir?
Well, and you know, in addition to the fact that it can generate electric power and it can whatnot, it also does have some very, very useful daughter products in the decay chain, such as radioactive molybdenum, which, also relevant to Utah, could be used at the Huntsman Cancer Center.
That's right.
And can make a tremendous, tremendous difference for those who do have cancer by being a very targeted therapy that only kills the stuff that needs to be killed. I had cancer once. Went through radiation, and they stick you in a great big X-ray machine, and they X-ray the snot out of you. It's an incredibly crude mechanism. If you can get a very smart tool to get that radioactive molybdenum directly to the cancer cell.
It's actually radioactive bismuth. Molybdenum
Bismuth.
is a diagnostic isotope.
Okay, the diagnostic.
Bismuth. What I want to tell you about, and I thought about this before I put these slides together. I would love to do a whole presentation where I just tell you about targeted alpha therapies for fighting cancer, because it's worth an entire presentation on its own. What it is, what he's talking about is, there is a particular substance that's formed from the decay of uranium-233 that has shown incredible promise against fighting cancer. They take this substance called bismuth-213, they append it to an antibody. They put this antibody in your body. The bismuth has a 45-minute half-life. It goes and it finds cancer cells. It lands on them like a little lunar lander landing on the moon, and it binds to them. Unlike a lunar lander or any other antibody, it's carrying a nuclear bomb with it. That nuclear bomb goes off. This alpha particle decays. The alpha particle only goes through about 2 cell diameters before it stops. But in those 2 cell diameters, it will kill whatever those 2 cells are. Now you got a 50-50 chance it's going to kill the cell you want to kill. That's good odds. That's good odds. So the idea is you put this stuff in, it's great against distributed cancers, leukemias, lymphomas. All the cancers that are the hardest kind for regular cancer fighting techniques to get are the perfect kind for targeted alpha therapies. Anybody know anybody who's suffering or dying from leukemia or lymphoma? I sure do. You know, it's a terrible, terrible struggle, and a lot of people are going to end up getting it. There may be a future where you go to Huntsman Cancer Center, and instead of them saying, all right, let's get you started on chemotherapy, let's get you started in radiation treatment, they're literally going to say, sit down, I'm going to shoot this in your body, and in 45 minutes, most of your cancer is going to be dead. How would you like to hear that?
That would be amazing.
That can literally be done. Let me tell you guys a true story. True story. Right now, we only have enough of this material separated at Oak Ridge National Lab to treat about 3 people a week. 3 people. And so only the people that are about to die get this. And they die anyway. But here's a true and tragic story. So I was talking to one of the people that did this, and she said, we injected this into a patient who was at stage 4 acute myeloid leukemia. And it killed 2 kilograms of leukemia in his blood. She said, to keep that in perspective, that would, if you tried to do it with chemo, you would destroy your kidneys just from the attempt. That would do it in right there. Killed 97% of the leukemia in one pass. This was in, a matter of a few hours. I said, what happened to this guy? She said, well, he died. I said, well, why did he die? She said, because we now have material to give him their 2nd or his 3rd or his 4th follow-up, like we would have done in any other situation. We would have given him the rest of the doses. We would have said, this is a guy in stage 4. This was a guy who was just about to die. And they killed all of that leukemia. Why? Because we did not have enough of that precursor material that came from uranium-233. Why? Because we don't have thorium reactors. If we had these machines running, I am not exaggerating when I say they would be producing a steady stream of medicine that would save tens of thousands of lives. And they would do this while they were making electricity. There would be no skin off their nose to do this at all. I think we should be working absolutely seriously. In the back right there.
But extracting that bismuth from this fluoride salt becomes energetically difficult.
Well, you extract the precursor. You extract the let me show you how this works. Okay. So you have 2 fluids in the salt. You have a fuel salt and you have a blanket salt. In the blanket salt is the thorium. That's thorium-232, which is the common kind, the kind we use for making energy. The precursor to the medicine is called thorium-229. It's the decay product of uranium-233. It's present in the fuel salt. So if you see thorium in the fuel salt, you know it's the medicine, not the fuel. And you can chemically extract it from the fuel salt, set it aside, go send it up to Huntsman. And what they do is they milk that thorium-229 regularly to extract actinium-225, which has a 10-day half-life. That's the precursor. That's what you send to the hospitals. Then they extract every 45 minutes the bismuth-213 that is then coupled with the antibody and injected in the patient. What we've got to get is the thorium-229. That's the precursor. Once we have that out, that's the part they have half a gram separated at Oak Ridge right now that treats 3 people a week. If we could get that stuff out and separate it and send up to cancer centers, we could just be treating patients steadily from that material.
And then
it's beyond patent. This has been out.
And then the radioactive molybdenum is used for detecting the presence of the cancer.
They use that for all kinds of scans, bone, gallbladder, heart.
And that's also a daughter product.
Yes, in the back.
So there are other ventures working on thorium, TerraPower and Martingale. Are those very different approaches to what you're talking about here?
Yeah, actually, I was sitting with TerraPower last week at a White House meeting. They're not using thorium. They're not doing a thorium reactor. They're doing a molten salt reactor, but it's based on uranium and chloride salts. Very, very different than what I presented here. Also, the Thorcon approach you're talking about, also very different. It's based on a single fluid. It's not based on the efficient use of thorium. They're going to basically burn uranium-235, and that's my big difference with their approach. It's not an efficient use of thorium. It's not going to achieve those goals of having hundreds of thousands of years of fuel. It's also not going to achieve the goals of being able to get the medicine out. Any medicine they form is lost in a billion atoms of thorium-232, so they can't get the medicine either. I have designed this reactor specifically to do a number of missions simultaneously and to do them as best as they possibly can be done. And this is where I differ with a lot of my competitors, is they're taking shortcuts. They're doing things, they want to go fast, but they're doing it wrong. This is how we did it back in the 50s with uranium reactors, and we're still paying the price 70 years later. Do it right from the beginning. Yes?
You said these are a lot smaller. You said they're able to be manufactured in a factory instead of on site. How big are they actually, and how easy is it to implement them around the world?
Well, this is not perfect, but it's a pretty good sense of about the size of the reactor, its primary containment vessel, the power conversion system, the chemical processing system. I mean, if you were to see this vis-a-vis an existing reactor, this is really pretty compact, pretty tiny. So, we got a lot of questions.
Are you worried about the toxicity of beryllium chloride?
No, because I'm going to be dissolving in stuff that's so much more toxic than that it really doesn't matter. If beryllium chloride toxicity was my concern, I got things a whole lot worse.
Well, if all this bad stuff ruptures, then what?
Well, this is under low pressure. This isn't going to spray or anything. In fact, it'll probably seal its own hole from the fact it'll freeze and plug the hole. They noticed that a couple of times with the molten salt reactor experiment. That because it was operating under low pressure, if there was a damage or a rupture, it pretty much scabbed over and kept going. So,
What's your estimated cost to build the prototype before you get to one that's actually generating massive?
I would estimate that a prototype like this would probably be somewhere between $1 to $2 billion in development cost. It's going to be a serious undertaking. Yeah.
Where are you at right now in the process?
Right here. BYU, talking to a bunch of smart people. We got a lot of work ahead of us. There's no doubt about it. Yes, sir.
Do you have any project or whatever, like even ballpark? And then second, what is the process for extracting spent fuel and processing it? And how do you?
I have the slides for that. Let's actually touch on that afterwards, because I think some people need to go. Right. But I'm really focused on how do I make this more profitable? How do I make this a more attractive development, both for governments, for investors, et cetera, rather than worrying about how much is it going to cost per megawatt hour? How do I think if we were worried about making power plants more profitable, we would be shutting down nuclear reactors right now. They're getting shut down because they're not profitable enough. Do you have any final questions? One or two more?
I would just like to suggest to the young lady's question earlier is on your website, you have the one pager on the 10 advantages. When you want to go talk to other people who've never heard of this and get them interested, that is a good document, plus some of your YouTube videos. That old one that's like an hour long. I don't know many people who've actually watched that who
probably you to watch
it. Okay.
And that
so
could
there is some
educate.
stuff out there on your website.
That's
Okay,
awesome.
one more
That could
question? Young man.
So I got some questions. How many of your reactors could you fit in, say, one coal-fired plant? And the second question is, how many coal-fired plants would it take to produce the same amount of energy that one of your plants would?
Well, I mean, if I was comparing it to the site in Delta, the IPP site,
sure.
Within the existing footprint of the plant, we could probably fit 10 or 15 of these reactors, which would produce quite a bit more power than the plant does now. But there's plenty of room. We don't have to tear anybody's thing down. There's a lot of open space down there in Delta.
Let's give Kirk a hand.